Hello, my name is David Schultz. Welcome to Our Earth, its climate, history, and processes. In this lecture, I want to talk about the generation of magma. Recall the question that I posed in the last video. If the upper asthenosphere is only about 1% melted, and the mantle as a whole is largely a solid, then where does this magma, this liquid rock, come from? Before we answer that question, we need to review the difference between felsic and mafic rocks. Remember that felsic rocks are primarily composed of feldspar and silica. These are the granites, the rhyolites. These tend to be less dense, have more silica, and as a result have lower melting temperature. On the other hand, there are the mafics. These are the magnesium iron rocks, the gabbros, and the basalts that we see primarily compose ocean crust. These are more dense, they have less silica, and as a result have a higher melting temperature. So, coming back to the generation of magma and its expression at the surface, let's talk about volcanoes. Volcanoes are the surface expressions then of the extrusion of magma onto the surface. There are three places geologically where these volcanoes occur: hotspots, mid-ocean ridges, and subduction zones. And we're going to look at each one of these three separately and look at what causes magma generation in each one. The first one is the hotspot, and what this is a slender cylinder of warm rising mantle, remember solid, but it's less than, say, about 100 kilometers in diameter. These are called diapirs or mantle plumes. They appear to originate from deep within the mantle, possibly even as deep as the boundary between the mantle and core itself. And we know this from looking at the helium isotopes within the magma itself. Typically, these mantle plumes are 200 to 300 degrees C warmer than the surrounding mantle, and this gives them the buoyancy that allows them to ascend up towards the surface. These plumes may be responsible for uplift. Since they're rising and they're more buoyant, they could lift the Earth's crust up to 1 or 2 kilometers higher, although we don't really have all that much evidence for that, but it appears to be consistent with these rising mantle plumes. We also may see these plumes responsible for flood basalts, and these may actually precede episodes where the continent is splitting apart. And finally, the rising of this hot magma from deep within the mantle will lead to regional scale metamorphism due to the added heat being brought here. This is the location of flood basalts that have been linked to regions, hotspots on the globe over time. You can see them at Yellowstone, Iceland, Siberia, Deccan flood basalts in India, and as well as other places around the globe. We're going to talk about two examples. In the Google Earth tour, you'll see specifically the hotspot that actually happens to coincide with the plate boundary, the mid-ocean ridge. This is the Iceland example. The second example is a hotspot within the middle of a plate, and this is the example from Hawaii. So if we look at the locations of seamounts or underwater extinct volcanoes in the Pacific, we see a chain that extends from the Aleutian Islands southward, and those seamounts are called the Emperor seamounts. And if you date the age of those seamounts, you'll see that they end up being about 80 million years on the northern extent, all the way down to about 48 million years on the southern extent. Around 45 million years ago, we see a change in the orientation of the seamounts to what are now called the Hawaiian seamounts. And this seems to have happened around 45 million years ago. And what is believed to have happened during this time was that the plate motion changed relative to the hotspot. And you can see the most recent expression of this hotspot, this diapir of rising mantle being happening at Hawaii. The second place on Earth where volcanoes form are at mid-ocean ridges or spreading centers. Here, the magma forms in a different way. Rather than being forced up through the crust and forming a volcano at the surface that way, here we have what's called decompression melting. Where two plates are being pulled apart, the pressure on the underlying material reduces. This release in pressure causes part of the upper mantle to liquefy, and that produces the magma chamber underneath the spreading center. Because mafic minerals have a higher melting temperature than felsic minerals, these tend to precipitate out of the magma chamber. At the bottom of this magma chamber, you'll see a peridotite layer, which is a result of these mafic minerals crystallizing out and forming a column. Above that, we have the gabbro, the intrusive igneous rock, where this magma chamber cools. And then above that, we have what are called the sheeted dikes in the basalt. This is the extrusion of the remaining magma to the surface, forming these basalt pillows. Here are pictures from the National Oceanic and Atmospheric Administration showing the eruption of pillows here, and you can see the cracks in one of these pillows, much warmer than the surrounding rock, and that's why it's glowing red. The temperature in this rock is about 1200 degrees Celsius in the interior. Here are basalts that are cooled, and you can see the similarities, this bubble shape, that's the pillow lavas. So as these pillow basalts then are spread away from the center, sediments will fall on them, and that produces this layer where we go from sediments, the sheeted dikes in the basalt and the pillow lavas, to gabbros, to the peridotite layer, to the mantle. And that column is called an ophiolite sequence, and we'll hear more about those ophiolites in the rest of this course. Also, as these pillow basalts come in contact with the water, they cool quite quickly. That's why they have relatively small grains. And there's also these sheets and seawater that's able to flow into and between these pillows into the dikes and allow recirculation of seawater. And so we'll get these smokers and exchanges of minerals occurring between the cold seawater and the seawater that then filters down, becomes heated, and then is extruded again through these smokers. The third place where volcanoes are seen on Earth is in subduction zones. Here we've got the plate going down, and it's carrying the sediments into the trench, and as this plate descends into depths, the pressure on it increases, the temperature increases, and we have partial melting of this plate, leading to the production of magma. And here, this is called fluid-induced melting. It's called fluid-induced melting because as this oceanic crust goes down, it carries sediments with it, and in between these sediments lie water. The water that's trapped between these sediment grains causes a lowering of the melting temperature, and this allows melting of these sedimentary rocks to occur as they descend. And so what you'll see then is as this plate goes down into the trench, it heats up, partial melting of the sediments occurs, and then this results in the rise of magma up to the surface, producing what are called island arc volcanoes, parallel to the subduction zone, but on the subducted side of the plate. And so these magma then is composed of an intermediate composition between the descending plate and the stuff that's melted as this magma rises up. So to summarize today's lecture, we saw that magma and volcanoes are created in three ways. We have hot spots that rise up from probably the mantle core boundary, rise up through the mantle as solid, reach the surface, and then result in partial melting, which then reaches the surface. The second way that magma is created is decompression melting at mid-ocean ridges. Here, where the plates are spreading apart, the pressure on the underlying mantle lowers, and this results in partial melting. The third way that magma is created is by fluid-induced melting at subduction zones. Here, sediments lying on top of the subducting plate lowers the melting temperature of the rock, and this leads then to the production of magma.